Imagine a 400-pound, water-gorged, spike-covered biological machine just dripping with acidic fertilizers, swaying precariously on a freezing urban balcony.
Yeah, that's a terrifying mental image.
Right. Now imagine trying to bolt that monster to the concrete so it doesn't crush you or, your downstairs neighbor in a windstorm.
Ah,
Today, we aren't talking about planting a few sunflower seeds and just hoping for rain. We are talking about the hardcore mechanical and chemical engineering required to bend nature to your absolute will.
exactly. I mean, we are looking at an approach that discards the entire concept of natural surrender. You stop waiting on the seasons, and you start building a highly calibrated system.
Welcome, everyone, to another deep dive. Today, our mission is to take you on a journey to the absolute limits of what is possible to grow, regardless of where you live. We're going to unpack how you can manipulate thermodynamics, structural engineering, advanced soil chemistry, and the literal cycle of the sun to cultivate something as massive and exotic as a tropical dragon fruit vine.
And doing all of this within seemingly impossible constraints. Like, we are talking about forcing a jungle epiphyte to thrive in a cold climate concrete jungle.
Yeah, treating a plant of that scale, not as a passive organism, but like a complex machine.
Mhm.
Every single gear, the ambient heat, the physical support structures, the ionic balance in the soil, the duration of light, it all has to be engineered.
It really does. And to figure out how to calibrate those gears, we're looking at a surprisingly bizarre but completely fascinating stack of sources today.
Oh, the sources are wild.
Yeah.
We've got landscape design data on frost protection from a group called Thrive Lot. We have highly specific urban gardening manuals from Life Tips.
Which are surprisingly technical, by the way.
Very. We've got a brilliant DIY structural trellis guide from Rare Dragon Fruit. We're also diving into a hardcore agricultural science paper published in Frontiers in Plant Science, a botanical study from Hort Science, and I love this part, an industrial engineering spec sheet from ITW Redhead on seismic-rated concrete anchors.
Which, I know, initially feels completely out of place in a botanical discussion. But when you are dealing with a fruiting cactus that can live for 30 years and generate the kind of physical torque we are going to discuss, well, industrial hardware is the only thing standing between you and structural collapse.
Okay, let's unpack this, because before we can even think about the plant itself, we have to address the environment. If you live somewhere that gets cold, you can't just put a tropical cactus outside.
No, absolutely not. It'll just die.
Right, you have to bend the local climate. We have to start with the physics of microclimates.
And this brings us straight to the data from ThriveLot. Their analysis focuses on the synergy between a microclimate, which is, the localized weather conditions of a very specific small area, like a corner of your patio, and thermal mass.
Yeah.
We are essentially talking about building heat batteries.
Heat batteries, so materials that sit out in the sun, absorb solar radiation all day, and then slowly bleed that heat back into the surrounding air when the sun goes down and the temperature drops.
Precisely. And the ThriveLot data is uncompromising on this point. Water is the ultimate heat battery. To put it in perspective, dense materials like water can store 5 to 10 times more heat per unit of volume than typical insulation materials.
See, I always pictured thick stone walls or brick acting as the best heat sinks. It feels counterintuitive to use liquid.
Yeah, a lot of people think that. But the physics actually heavily favor the liquid. Water has an incredibly high specific heat capacity, fundamentally because of the hydrogen bonds between the water molecules.
Okay, so it takes a lot of energy to heat it up.
Right. It takes a massive amount of solar energy to force those molecules to vibrate faster and raise the temperature, and that energy doesn't disappear, it gets stored. Compare water to a solid block of concrete. Water can absorb and hold almost 5 times as much thermal energy as that exact same volume of concrete.
Wow. So we are essentially building giant hot water bottles for the garden.
That captures the mechanism perfectly, yeah. And the recommendations for deploying this are highly specific. Experts calculate that you need 2.5 gallons of water per square foot of growing space for every single degree of temperature increase you are trying to achieve.
Okay, wait, let me do the math on that because I want to visualize this for the listener. If I have a modest 100 square foot garden on a terrace, and I want to raise the ambient temperature by a mere 5 degrees Fahrenheit to survive an unexpected frost.
Which is a very common scenario.
Right. So I would need 1,250 gallons of water. Wait, no. 100 square feet times 2.5 gallons times 5 degrees. Yeah, that's 1,250 gallons.
Your math is correct. Though in practice, for localized protection, growers often use 55-gallon drums strategically placed in a tighter radius. The data shows that a single 55-gallon drum can raise the surrounding air temperature by 5 to 7 degrees Fahrenheit in an 8 to 10-foot radius.
Look, I have to push back here. A single gallon of water weighs roughly 8.3 pounds. A 55-gallon drum is over 450 pounds.
It's extremely heavy, yes.
So if you are asking an urban listener to put 4 or 5 of those drums on a cantilevered balcony to protect their plants, you're asking them to load over 2,000 pounds of dead weight onto a structure that was, honestly, probably only engineered to hold a couple of lawn chairs and a barbecue.
Mm.
That is a recipe for a catastrophic balcony collapse.
Oh, 100%. That is a very real, very dangerous structural limitation. You cannot blindly apply field agricultural techniques to urban architecture.
So what's the alternative?
Well, if space and weight limits make heavy water batteries impossible, or if you live in a chronically overcast region where water barrels struggle to absorb enough direct sunlight anyway, the Thrive Lot data points to alternative methods. This is where your intuition about stone comes back into play.
Okay. Even though the heat capacity is lower than water.
Right.
Wait, I assume stone is safer for the architecture and requires less maintenance, though.
Exactly. It requires virtually zero maintenance, and its durability is measured in decades. A permanent 6-foot south-facing fieldstone wall was shown in a USDA Zone 7B study to consistently increase ambient overnight temperatures by 4 degrees Fahrenheit for nearby citrus trees.
4 degrees is huge when you're skirting the freezing line.
It's the difference between life and death for a tropical plant. And concrete pavers placed around raised beds extended the growing season by 3 weeks in Colorado.
So it's a trade-off. Less thermal efficiency, pound for pound, but you don't have to worry about a plastic barrel cracking and flooding your downstairs neighbor's apartment.
Right. And there's also a third option for those dealing with ground-level urban yards where weight isn't the primary issue, but budget is, and that's earth mounds. Soils, particularly clay-heavy soils, are surprisingly effective thermal masses, holding 15 to 20 BTUs per cubic foot. The most advanced application of this in the data is hugelkultur.
Oh, I've seen the time lapses of this on gardening forums. People dig a trench, throw in massive logs covered in branches, and then pile dirt on top. It looks like a burial mound.
Yeah, it does. But it functions as a slow-release biological heater. You aren't just relying on solar radiation. As the buried wood and organic matter decompose, the fungal networks and bacteria aggressively break down the carbon.
Oh, so the rotting process itself generates heat.
Exactly. That microbial digestion is an exothermic reaction. It literally generates internal heat. An active hugelkultur mound can radiate heat from the inside out for 5 to 6 years. Plus, rotting wood acts like a sponge, holding 30% more moisture than a standard raised bed.
That's brilliant. But again, bringing this back to our listener on a 500 square foot urban patio, they cannot build a rotting log mound on concrete. They cannot build a 6-foot masonry wall. And they can't load 2 tons of water barrels without risking a structural collapse. Make that make sense for the urban grower.
For that specific constraint, the urban landscape designers recommend a multi-layered thermal mass system. You distribute the weight and maximize efficiency by combining a mid-layer of limited water storage, think sleek, flat, black water tanks that hold maybe 20 gallons, placed flat against a sun-facing brick wall with a surface layer of dense stone mulch covering the soil itself.
Oh, I see. So the black tanks grab the immediate solar radiation and handle the rapid temperature drops in the air, while the stone gravel on top of the pot traps the heat down at the root zone.
Exactly. And this specific hybrid combination has been proven to reduce frost damage by 28% in small urban setups, completely without exceeding municipal balcony weight limits.
I like where this is going. We've solved the temperature and weight problem. But there's a hidden cost to the water systems, isn't there? I mean, you can't just seal a black tank of water and leave it in the sun for 5 years.
No, the maintenance is non-negotiable. Stagnant water in a dark, warm container is a perfect incubator for algae. Furthermore, if you leave those tanks full during a deep winter freeze, the expansion of the ice will violently rupture the plastic. The guidelines specify draining the water seasonally and scrubbing the containers annually with a vinegar solution.
Right, because vinegar kills the algae without leaving toxic residue that might leak onto the plant.
It does. But the crucial detail from the data is how the frequency of that maintenance dictates the thermodynamics. Quarterly maintenance training, scrubbing the algae, and physically repositioning the surface stones to maintain their optimal angle to the shifting seasonal sun actually boosts the thermal efficiency of the entire system by 62% compared to doing it annually.
Wait, a 62% increase in heat radiation just by cleaning algae and moving rocks? Why is the drop-off so severe if you ignore it?
Because algae is exceptionally good at blocking light. A thin film of green algae on the inside of a clear or semi-transparent water barrel acts as an insulator, bouncing the solar radiation away before it can heat the water mass. And as stones settle into the soil, they lose the exposed surface area needed to capture sunlight. You have to keep the physical gears of the machine clean.
Okay, the microclimate is built. We have a thermally optimized, weight-managed, algae-free zone that tells winter to back off. Now, we introduced the biological payload. We are planting a dragon fruit vine. And according to the Life Tips manual, there is a very specific evolutionary reason why this massive tropical fruit is ideal for a concrete box in the city.
Yeah, when people imagine growing tropical fruit, they usually envision towering mango trees with massive taproots plunging 10 feet into the earth.
Yep.
You cannot put a mango tree on a balcony. But the dragon fruit, which is scientifically classified in the Hylocereus genus, is an epiphytic cactus.
An epiphyte, meaning it doesn't naturally grow in the ground at all.
Exactly. In its native jungle environment, it germinates in the crooks of tree branches or clings to sheer limestone cliffs. It survives by pulling moisture from the humid air and feeding on whatever leaf litter gets trapped in the bark. Because of millions of years of this evolutionary history, it never developed a deep taproot. Its root system is incredibly shallow, highly fibrous, and spreads out laterally.
Which makes it the perfect candidate for container growing. It doesn't realize it's trapped in a pot because it naturally prefers a confined, shallow space anyway.
Right. A standard 15 to 25-gallon fabric pot provides more than enough root space for a fully mature, fruit-bearing plant. And the other massive advantage highlighted in the Life Tips Guide is the biological timeline.
Right, because if I plant an apple seed today, I'm waiting a decade to bake a pie.
And if you plant a dragon fruit seed, you will wait 5 to 8 years, and the resulting fruit might taste like cardboard because the genetics of seeds are highly unstable. Serious horticulturalists completely bypass seeds. You start with a mature stem cutting.
You essentially clone a proven, delicious plant.
Exactly. A healthy cutting from a mature vine will establish roots in a few months, often flower by its second year, and deliver a robust commercial-level harvest by year 3. Furthermore, its fruiting mechanics actively reward the kind of aggressive pruning required in small urban spaces.
Make that make sense, because usually if I hack the branches off a fruit tree to keep it small, I'm cutting off the wood where the fruit was going to grow.
Yeah, with many fruit trees, you are destroying fruiting spurs that took years to develop. But dragon fruit biology operates differently. They bear their flowers exclusively on new growth that emerges from mature 1 to 2-year-old stems.
So if I have a main stem and I chop the end off because it's hitting the ceiling of my balcony, the plant panics.
It doesn't panic, it reroutes its energy. Apical dominance is broken. The plant stops trying to grow longer and instead pushes out 3 or 4 new side shoots from that mature stem. Those brand new side shoots are hyper-vigorous, and that is exactly where the floral buds will form.
Oh, wow.
Yeah, so pruning doesn't sacrifice your harvest. It chemically forces the plant to multiply its fruiting sites.
It actually thrives on being contained and managed. But before our listener runs to the nursery, we have to talk about genetics. Because the Life Tips Guide serves as a massive warning label here. Buying the wrong species of dragon fruit will lead to years of profound frustration.
Oh, absolutely. Botanical nuance is the difference between a massive harvest and an empty pot. There are 3 primary species dominating cultivation. The most prevalent is Hylocereus undatus.
Right. The classic white-fleshed dragon fruit, bright pink skin, green scales on the outside, and white inside with the tiny black seeds. It's what you see in every grocery store.
From an engineering standpoint, this is the most resilient model. It is exceptionally vigorous. It boasts the highest cold tolerance, able to survive brief ambient dips down to 35 degrees Fahrenheit without tissue necrosis, and crucially, it is self-fertile.
Meaning its own pollen can fertilize its own flowers. A solitary plant on a balcony will produce fruit entirely on its own.
Right. Now contrast that reliable biology with the second major species, Hylocereus costaricensis.
The red flesh variety, the one that stains your hands magenta when you cut it open.
Gastronomically, many prefer it. It possesses a richer sweetness, higher Brix levels, and dense antioxidant content. But there is a massive physiological catch. The vast majority of red varieties are self-sterile.
I really want to emphasize How devastating that is. You spend 3 years watering this plant, dragging it away from the frost, building trellises. It produces these massive, beautiful night-blooming flowers, and then the flowers just shrivel up, turn brown, and fall off. Zero fruit.
Because the pollen produced by a red dragon fruit flower is chemically incompatible with its own stigma. It requires cross-pollination from a genetically distinct plant nearby, like a white variety, blooming on the exact same night, with a pollinator insect to transfer the genetic material.
That's so stressful. If you only have room for one container on your patio and you mistakenly buy a self-sterile red variety, you have basically built a very complex, very heavy foliage plant.
A tragic waste of a microclimate, honestly.
What about the third option?
Hylocereus megalanthus, the yellow dragon fruit.
Oh, I've seen these at specialty markets. Smaller, bright yellow skin covered in actual thorny spines instead of those leafy scales.
And possessing a pronounced complex honey flavor. They are widely considered the superior tasting fruit. They are also self-fertile, which solves the pollination issue. But they are the prima donnas of the genus. They demand consistent ambient humidity between 50 to 70%.
Good luck getting that on a windy urban balcony.
Exactly. Furthermore, their epidermis is highly sensitive. Without shade cloth protecting them from intense afternoon ultraviolet light, the skin suffers severe sunscald, ruining the fruit.
Okay, so for the urban balcony engineer, the white-fleshed Hylocereus undatus is the undisputed choice for baseline reliability. Now let's talk about the soil. Because if this plant evolved clinging to limestone cliffs and the crooks of jungle trees, digging up a shovel full of generic potting soil from the hardware store is going to end in disaster.
Yeah, generic potting soil is designed for petunias and tomatoes. It is formulated to hold water. If you pack an epiphytic cactus root system into dense, water-retaining peat moss, you immediately create an anaerobic environment. The roots suffocate, opportunistic fungi take hold, and the plant rots from the base up within weeks.
Because the roots physically need to breathe oxygen.
They require massive aeration and rapid drainage. The Life Tips Manual outlines a custom, highly porous, mineral-rich matrix that mimics the sheer face of a cliff. The proportions are exact.
Walk us through the recipe. Let's build this dirt.
Okay, so 40% coarse perlite or pumice. This provides the structural framework, ensuring the soil never compacts and water flushes through instantly. 30% screen compost or high-quality coconut coir. This provides the necessary organic matter for nutrient breakdown and offers just enough slight moisture retention so the plant doesn't desiccate in the summer wind.
Noticeably absent is peat moss.
Peat moss is an absolute hazard here.
Yeah.
When peat dries out, it becomes hydrophobic. It literally repels water. Worse, as it breaks down, it drastically acidifies the soil. Dragon fruit demand a near-neutral pH between 6.0 and 7.5.
Which brings us to the next two ingredients.
Right. 20% crushed granite or porous lava rock, specifically sifted to 1/8 to 1/4 inch chunks. This provides the trace mineral environment the roots evolve to seek out. And finally, 10% horticultural charcoal.
Charcoal, like the stuff from a fire pit.
Horticultural activated charcoal. It acts as a chemical filter. It absorbs impurities from urban tap water, keeps the soil matrix sweet by preventing bacterial buildup, and creates microscopic condominiums for beneficial soil microbes.
Okay, we have our cliff face rock soil loaded into a breathable 15-gallon fabric pot. We plant our white dragon fruit cutting. Now, how do we operate the hydrology? Because my instinct tells me, it's a cactus, put it in the sun and ignore it.
And that instinct is responsible for more crop failures than almost any other variable. Assuming cactus means desert survivor fundamentally misunderstands the epiphyte. They experience distinct wet and dry seasons in the jungle canopy. You have to manually replicate that hydrological rhythm.
Unpack that rhythm. How do I water this machine in the spring?
As spring temperatures rise above 60 degrees Fahrenheit, the plant exits dormancy. You water deeply, thoroughly saturating the pot, but only when the top 2 inches of the pumice mix are bone dry to the touch. It is a cycle of flood and dry. But as we approach June and July in the northern hemisphere, we enter the pre-flowering stage. This is the most delicate biological tightrope.
What changes in the summer?
The plant requires artificially induced drought stress.
You have to torture it.
Controlled stress, yes. You must maintain even but extremely low moisture. You stretch the dry periods. Biologically, the plant senses the lack of water and perceives a threat to its survival. That threat triggers a reproductive panic. It redirects its energy from growing longer vines into forming flower buds to ensure its genetic legacy before it supposedly dies.
But if I withhold too much water,
The plant decides it doesn't have the internal reserves to support giant water-filled fruits. It will literally abort the buds. They will yellow and drop off. But if you panic and overwater it during this stage, the plant decides the environment is lush and safe, aborts the buds anyway, and goes back to growing green vines.
You're literally holding the plant hostage. Stress it just enough to force it to reproduce, but give it just enough water so it doesn't abandon the mission.
And the moment those massive flowers open, which, by the way, only happens for a single night and the fruit officially sets, the rules flip entirely. You are now responsible for swelling fruits that are 80% water. You transition to deep watering 1 to 2 times a week. If you underwater during fruit development, you will harvest fruits the size of golf balls.
It is exhausting just thinking about it. Let me ask a logistical question, though. Suppose a listener doesn't want to wait years for a cutting to mature. They go to a high-end nursery and drop $150 on a massive 3-year-old dragon fruit vine jammed into a plastic nursery pot. They bring it home to their balcony. Can they just rip it out of that plastic pot, shake all that terrible generic nursery dirt off the roots to save space, and jam it bare root into our custom pumice mix?
No, that is a fatal error. You never bare root a mature dragon fruit plant unless you are performing emergency surgery to cut away severe root rot.
But the nursery dirt is garbage. It's full of peat moss.
It is, but the plant's entire microscopic root hair system is currently integrated into it. Those fine, fibrous roots are incredibly fragile. Bare rooting rips away those microscopic hairs. The shock to a mature plant is so profound that it will completely shut down. It will divert all its energy for the next 12 to 18 months simply trying to regrow its root network. You will lose an entire year of flowering.
Wow. So how do you transplant the 400-pound beast?
With surgical delicacy. You slide it out of the plastic. You gently tease the outer circling roots loose with your fingers. You trim any obvious black or mushy tips. Then you submerge the entire intact root ball in a bucket of room temperature water for 20 minutes. This deeply rehydrates the core and gently loosens the outer layer of old soil without tearing the root hairs. Then you nestle it into the new pot and surround it with your custom pumice matrix.
We really are operating on a biological machine here. And as this machine thrives in our perfect soil and microclimate, we hit a wall of physics. Because a mature dragon fruit canopy is not a delicate string of pearls trailing over a pot. The data says this thing can weigh 200 kilograms.
Easily upwards of 400 pounds of dense, water-heavy, photosynthetic flesh.
400 pounds. You cannot lean a 400-pound cactus against a balcony railing. You cannot tie it to a plastic bamboo stick. The structural engineering required here is intense.
It is absolutely non-negotiable. Dragon fruit stems are heavy and they lack the woody lignin that allows trees to stand upright. If they lack a rigid anchor, gravity just pulls them to the ground. They sprawl across the concrete, shading their lower sections, which halts photosynthesis. Worse, the constant microabrasions from dragging on the ground open wounds for fungal infections.
Right, so the structure is as important as the soil. Let's look at the DIY trellis guide from rare dragon fruit. How do we build a skeleton for a 400-pound organism?
Well, the industry standard and the most efficient use of vertical space is the single pole trellis. It creates the iconic umbrella canopy.
It looks like a weeping willow, but made entirely of spiked green tentacles.
Yeah, exactly. It begins with an unyielding central column. This isn't a garden stake we're talking about. We're talking about a 6-inch PVC pipe filled to the brim with wet concrete, a chemically treated 4x4 hardwood post, or a precast concrete pillar. You place this column directly into the center of the 15-gallon pot, plant your cuttings around the base, and manually train them straight up the pole,
Tying them as they grow.
using soft, wide horticultural tape or twine. Never use zip ties or thin wire, as the heavy stems will grow over them, slicing into the flesh and severing the vascular tissue. As the stems climb, they sprout aerial roots that grip the concrete or wood, anchoring themselves. But the real engineering genius happens when they reach the top of that 5-foot pole.
Because they have to go somewhere. And the Rare Dragon Fruit Guide doesn't recommend buying a delicate wooden lattice for the top. What is their brilliantly redneck solution?
They utilize recycled motorbike tires or thick mountain bike wheel rims.
A literal motorcycle tire sitting on top of a cactus.
It sounds absurd, I know, but physically it is flawless. They drill heavy holes horizontally through the top of the central post, drive 2 thick pieces of steel rebar through to form a cross, and lay the rubber tire flat over the rebar.
The rubber is weatherproof, it won't rot, and it has a wide, soft curve.
And that curve is the secret. When the climbing vines reach the top, they are guided up through the hollow center of the tire. Once they clear the top edge, gravity takes over. The immense weight of the fleshy stems causes them to bend outward and drape down over the curved rubber edge.
Creating the weeping willow umbrella shape.
Right. But the shape isn't just aesthetic, it actually triggers a profound biological reaction. When the thick stem bends heavily over the curve of the tire, that physical stress creates microscopic cracks in the vascular tissue exactly at the apex of the bend.
Wait, breaking the plant's internal plumbing is a good thing.
In this specific location, yes. The physical stress and microcracking interrupt the flow of auxins, the plant hormones that dictate upward growth. The pooling of these hormones, combined with the physical stress at the bend, acts as a massive signal to the plant's DNA. The mechanical stress literally translates to a chemical command. It says, "We have reached the maximum structural height. Cease vegetative climbing. Initiate reproduction immediately." The plant will erupt with floral buds right at the bend over the tire.
That is staggering. The physical architecture of the tire is serving as a hormonal trigger. We are using mechanical engineering to force a biological response.
It is the perfect symbiosis of structure and biology. Now, the single pole is standard, but the guide also details the fence trellis.
For urban spaces, this makes sense. If you have a solid brick wall or a heavy structural balcony divider, you mount heavy wire mesh grids horizontally, and the plant climbs up flat against the wall, then drapes over the top rail.
But this brings us to the most dangerous variable, which is the live load.
Right. We have the static dead load, the 400 pounds of plant just sitting there. But a balcony isn't a vacuum.
When a severe thunderstorm rolls through an urban corridor, the wind whips between the high-rises. That massive umbrella canopy of dense hanging stems acts like a solid green sail. A 40-mile-per-hour gust, catching 400 pounds of high-up weight, creates immense, violent torque at the base of the trellis.
If I try to secure that wall grid or bolt the base of that massive wooden single pole directly to my concrete patio floor using standard masonry nails or those little plastic drywall anchors from a hardware store kit,
They will shear off instantly, or they will pull straight out of the concrete dust, and a 400-pound spiked biological wrecking ball will smash through your sliding glass door.
which perfectly explains why we have an industrial spec sheet from ITW Redhead in a botanical research stack. When you are fighting live load wind shear on a 400-pound water machine, you need commercial-grade construction hardware.
You must secure the base of that post. If you are drilling down into a concrete patio pad to mount a steel post base, the engineering specs demand the Trobolt wedge anchor.
Walk me through the physics of a wedge anchor. How does it hold that much torque?
Well, you drill a precise hole into the concrete. You hammer the anchor bolt into the hole. At the bottom of the bolt is a split expansion ring. As you take a wrench and tighten the hex nut on the top of the bolt, it physically pulls the tapered bottom of the bolt upward through that expansion ring. The ring is forced outward, violently crushing and expanding against the rough interior walls of the drilled concrete hole.
It essentially fuses with the stone through sheer mechanical friction.
Immense friction. The ITW Redhead data shows that a single half-inch diameter Trobolt anchor installed properly in 2,500 side-cracked concrete boasts an ultimate pull-out strength of 4,980 pounds.
Almost 5,000 pounds of vertical resistance. You could literally suspend a mid-sized SUV from that single bolt.
It will not fail under wind shear. But holding power isn't the only metric. The environment at the base of this trellis is hostile. It is constantly drenched in water, exposed to humic acids from the organic soil, and repeatedly soaked in concentrated chemical fertilizers.
If you use a standard zinc-plated steel bolt from a big box store, what happens?
The chemical salts in the fertilizer will initiate galvanic corrosion. The zinc coating will fail in wicks, the carbon steel will rust, swell, crack the surrounding concrete, and eventually snap under the torque. The ITW specs explicitly mandate the Trobolt plus SS for this environment.
SS stands for stainless steel. But all stainless isn't the same, is it?
Not at all. The spec demands Type 316 stainless steel. Standard 304 stainless will still pit and corrode when exposed to heavy chlorides, which are abundant in fertilizers. Type 316 contains an addition of 2% to 3% molybdenum.
Molybdenum, a heavy metal additive.
It drastically stabilizes the chromium oxide layer on the steel, making it practically immune to the specific chloride pitting corrosion caused by agricultural chemicals. It is the exact same marine-grade steel they use on deep-water oil rigs.
Okay, so the base is locked to the floor with oil rig hardware. What if I'm doing the fence trellis? I need to mount heavy steel wire grids to my vertical brick or concrete wall. I can't use wedge anchors for a thin grid.
For flush mounting fixtures to vertical masonry, the spec sheet points to Tapcon concrete anchors.
Those are the heavy-duty threaded screws you drive directly into the masonry.
You drill a pilot hole and drive the screw. But the thread geometry is crucial. The ITW data details their advanced thread form technology. Unlike a wood sprue that just pushes fibers aside, these threads actually cut a deep, mated groove directly into the concrete aggregate, creating an interlocking mechanical hold along the entire shaft of the screw.
And how do they survive the constant acidic water splashing on them?
They are coated in a proprietary blue Climaseal polymer. It acts as a dielectric barrier, preventing the chemical fertilizers from ever touching the carbon steel core. It is designed to survive thousands of hours in a salt spray testing chamber.
I want the listener to hold this entire mental image. You have a 15-gallon breathable fabric pot. Inside the pot, a heavy chemically treated timber post plunges down, locking into a steel base plate that is bolted directly into the concrete floor using 316 stainless steel molybdenum wedge anchors capable of holding 5,000 pounds.
Surrounded by a hyper-draining matrix of pumice, granite, and activated charcoal.
Right. On top of the post sits a recycled motorcycle tire bolted to a steel rebar cross. Draping over that tire is 400 pounds of fleshy, water-gorged cactus whose micro-cracked vascular tissue is screaming at it to produce fruit. And surrounding the base are black water tanks and stone mulch, passively radiating heat into the freezing night air.
It is a fortified, seismically stabilized, climate-controlled botanical fortress.
It is a masterpiece of urban survival. But a fortress alone does not generate maximum yield. We have the heat, the dirt, and the steel. Now, we have to turn the machine on. We have to fuel it.
And we transition from physics to chemistry. We look at the data from the Frontiers in Plant Science study on precision fertilization, because you cannot just dump a scoop of generic blue miracle powder onto a machine this sophisticated and hope for the best.
That study didn't just guess at the nutrient ratios. The methodology they used, response surface methodology, and something called a box-Benkin design, it sounds like advanced aerodynamics, not gardening.
It is advanced statistical modeling adapted for agriculture. When you test fertilizers, you are managing three massive variables: nitrogen, phosphorus, and potassium, or NPK. If a scientist wants to physically test every single possible combination of low, medium, and high levels of those three elements, the sheer number of test plots required would require acres of land and years of data collection.
It's too slow and too expensive.
So statisticians invented the box-Benkin design. Instead of testing every combination, the algorithm tests very specific midpoints along the edges of a theoretical 3D cube of data, plus a few center points. It uses the results of those specific plots to generate a three-dimensional mathematical map of the plant's biological response.
Okay, I'm picturing a sound engineer sitting at a massive mixing board in a recording studio. You have three main sliders controlling the track: nitrogen, phosphorus, and potassium. If you just jam all three sliders to the absolute maximum, the track doesn't sound better. It distorts, blows out the speakers, and ruins the song.
In botanical terms, jamming them to maximum causes severe fertilizer burn, destroys the soil microbiome, and wastes enormous amounts of money as the excess washes away.
And if you drop all the sliders to zero, you get silence. No fruit. The box-Benkin math is the algorithm that scans the mixing board and finds the absolute perfect, harmonious position for each of those three sliders to extract the loudest, clearest, most perfect song from the plant.
That is exactly how the 3D response surface works. It pinpoints the mathematical peak of biological production. And when the scientists ran this model on dragon fruit, the results fundamentally altered how commercial growers operate.
Because the perfect settings on the soundboard change depending on the color of the fruit.
The divergence is radical. The white-fleshed Hylocereus undatus and the red-fleshed Hylocereus costeracensis require completely different chemical diets to hit their maximum yield.
Let's look at the white pulp variety first, since that's what we planted on our balcony. To hit the mathematical peak yield, which the study logged at an unbelievable 25.5 tons per hectare.
A staggering volume of biomass.
To hit that peak, where do the N, P, and K sliders need to be set per plant, per year?
The optimized formula requires 400 grams of nitrogen, 300 grams of phosphorus, and a massive spike of 650 grams of potassium.
650 grams of potassium. It dwarfs the other two elements. Why is the white dragon fruit so violently hungry for potassium?
Well, at a cellular level, potassium is the master regulator. It doesn't physically build the plant tissue like nitrogen does. Instead, it acts as the primary osmotic pump. It floods the plant's cellular vacuoles with ions, which draws in massive amounts of water, physically stretching and elongating the cell walls.
Oh, it's the mechanism that physically inflates the fruit to make it huge.
Precisely. Without that massive 650-gram dose of potassium, the white dragon fruit lacks the hydraulic pressure to swell. Now, compare that to the red pulp variety.
The red variety actually hit an even higher maximum yield in this study, right? 35.6 tons per hectare.
It did. But to unlock that 35-ton yield, the sliders shift dramatically. The red variety's peak formula is 700 grams of nitrogen, 400 grams of phosphorus, and only 350 grams of potassium.
That is wild. The nitrogen need almost doubles to 700 grams, and the potassium demand is cut almost in half. Why the massive shift?
The red variety's genetic pathways are entirely different. The synthesis of those deep magenta pigments, the betalains, and dense antioxidants requires intense enzymatic activity fueled by nitrogen. Furthermore, the red variety naturally prioritizes aggressive vegetative vine growth to support its fruit, demanding heavy nitrogen to build the pyrrole rings in its chlorophyll.
Wait, if I take my white flesh plant and I accidentally feed it the 700-gram nitrogen diet meant for the red variety,
You will grow an incredibly lush, violently green, massive cactus that produces almost no fruit. The excess nitrogen tells the plant to focus on leaves, not reproduction. It is precision chemistry.
Okay, I have a practical execution question here. I look at my box Benkin map. I see I need 400 grams of nitrogen, 300 of phosphorus, and 650 of potassium for my white plant. Can I just mix those exact weights in a bucket on March 1st, dump it all into the fabric pot, water it in, and walk away for the year?
Doing so would chemically scorch the shallow root system, and 80% of those nutrients would leach out of your highly porous pumice soil before the plant could ever absorb them. The Frontiers study mandates splitting that exact yearly dosage into 4 distinct, seasonally timed applications.
We have to sync the chemistry to the plant's metabolic timeline.
Right. You are feeding specific systems as they activate. The first application is in March, as spring warming breaks dormancy. The scientists recommend a 10-40-40 split.
So only 10% of the total yearly nitrogen, but 40% of the phosphorus and 40% of the potassium. Why front-load the P and K?
Phosphorus is the core building block of ATP, the energy currency of the cells, and essential for root development. You are fortifying the root system and vascular plumbing before the intense growth begins. The second split hits in June, right as the pre-flowering stage begins.
This is when we are applying the drought stress.
Exactly. And while you are stressing it with low water, you hit it with a 20-10-45 split. You deliver almost half of its yearly potassium requirement exactly as the floral buds are initiating, ensuring it has the osmotic power to swell the impending fruit.
It's like loading a cannon right before you fire it.
Then comes the October split, post-harvest. The plant is exhausted. The split is 40-30-0.
Zero potassium in October, and a massive 40% dose of the yearly nitrogen.
The fruiting cycle is over. There is nothing left to swell. Applying potassium now is a complete waste. The plant desperately needs nitrogen to rebuild the vegetative tissue it sacrificed to make the fruit. Finally, a moderate 30-20-15 split in January sustains the baseline metabolism through winter dormancy.
We are conducting a symphony of cellular biology. We control the earth with pumice. We control the water with timed drought. We control the physical structure with molybdenum steel anchors. We control the cellular inflation with box Benkin mapped potassium.
We have engineered every tangible variable, which leaves only the intangible.
The final frontier. The ultimate flex over nature. We have to control time. We have to hack the literal rotation of the earth and the cycle of the sun.
And for this, we turn to the fascinating Hort science study on photoperiod manipulation.
The study classifies dragon fruit as a long-day plant. In botanical terms, how does a plant actually know how long the day is? It doesn't have eyes.
It has something vastly more sensitive. It has a phytochrome system, a network of light-sensitive proteins that measure the ratio of red to far red light. But ironically, long-day plants don't actually measure the daylight. They measure the duration of uninterrupted darkness.
They measure the night.
They do. In its natural cycle, dragon fruit only flowers between May and October. Following the March equinox, as the nights get shorter, the dark period falls below a critical threshold. The phytochrome system signals the plant's DNA, which in turn commands the meristems.
Hold on. Define meristems for the listener.
Oh, sure. Meristems are essentially the plant's blank stem cells. They reside in the areoles, those small fuzzy bumps along the cactus stem where the spines emerge. These blank cells can become either a new green branch or a flower bud. When the night becomes short enough, around 12 hours, the chemical signal flips the switch. It tells those blank stem cells stop making green vines and start building the complex architecture of a flower bud.
So it's basically saying summer is here, it's time to reproduce. And conversely, after the September equinox, when the nights drag on longer than 12 hours, the signal flips back. Winter's coming, shut down the flower production, focus on surviving.
Exactly, the season naturally ends.
But our engineered balcony machine doesn't accept natural endings. We want fresh dragon fruit in December. How do we override the sun's timer?
Commercial growers utilize a brute force biological hack called night breaking.
It sounds like psychological warfare.
It is physiological manipulation. If the plant requires a long, continuous period of darkness to trigger its winter shutdown, you simply break that dark period in half. You apply artificial light in the dead of night.
Are we talking about installing massive, blinding stadium floodlights on our urban balcony? Because my neighbors will call the police?
No, that is the brilliance of the phytochrome system. It is exquisitely sensitive. It doesn't require the intensity of the sun to reset the timer. The Hort Science study achieved massive success using standard low-output incandescent bulbs or 28-watt warm white fluorescent lamps.
A standard 28-watt bulb, you just string that up over the plant.
Roughly 30 centimeters above the canopy. You wire it to a simple timer. It turns on for 4 to 6 hours during the deepest part of the night, typically from 10 p.m. to 2 a.m.
Let me trace the plant's experience here. The sun sets at 5 p.m. in December. The plant starts counting the dark hours. 5 hours go by. The plant thinks, okay, winter night, keeping counting. Then, at 10 p.m., a 28-watt bulb flicks on.
The phytochrome system registers the light, and the internal dark timer instantly resets to 0.
Then at 2 a.m., the bulb turns off. It's dark again until sunrise at 7 a.m. Another 5 hours of dark.
Right, and because the plant never experienced a continuous block of darkness longer than 5 hours, its chemical logic dictates the nights are incredibly short. It must be the summer solstice. Keep commanding the meristems to build flowers. The Hort Science study demonstrated that an astonishing 88% of the plant's shoots produced flowers in the dead of winter using this exact hack.
We are rewriting its internal reality with a 28-watt bulb. That is incredible. But the study points out a massive caveat to this timeline. It isn't just about tricking the light sensors. The ambient temperature heavily dictates how fast this hack actually works.
This is exactly where amateur engineers fail. The time required for night breaking to successfully force a flower bud depends entirely on how cold the air is around the plant.
Give you the stark difference in the numbers.
Okay. In late fall, mid-October to November, when the ambient temperature is cooling but still relatively mild, it only takes 4 weeks of night breaking to force the meristems to push out a bud. The biological response is swift.
But what happens when we try this in the dead of winter? January or February?
When the temperatures plunge, that same 28-watt light bulb requires 3 full months of continuous night breaking to force a flower.
3 months?
Yeah.
Why the massive delay? Does the phytochrome system freeze?
No, the light sensors work perfectly. The bottleneck is the plant's core metabolism. Dragon fruit utilizes SAM photosynthesis crassylation acid metabolism. Unlike normal plants that open their pores during the hot day, cam plants keep their stomata tightly closed to prevent water loss. They only open their stomata at night to absorb CO2, storing it as malic acid until the sun comes up to process it.
So they breathe at night to save water.
Exactly. But the data reveals a critical flaw. When nighttime temperatures drop between 10 and 15 degrees Celsius, roughly 50 to 59 degrees Fahrenheit, the enzymes responsible for capturing that CO2 become incredibly sluggish. The plant's overall CO2 uptake plummets by 50%.
The plant is literally shivering. It's breathing at half capacity.
Its entire cellular machinery is moving through molasses. So the light bulb is screaming at the DNA, "It is the middle of summer. Build flowers immediately." The DNA sends the signal, but the cellular workers building the bud are operating at half speed because they are starved for processed carbon. It takes them 3 agonizing months to build what usually takes 4 weeks.
Which perfectly circles back to why we built the massive thermal water batteries and hugelkultur mounds in the first place. If you keep the microclimate warm, the CAM photosynthesis keeps humming, and the light hack works faster.
Every single gear in the machine relies on the others.
Let me just step back and summarize the sheer scale of the mastery we've just outlined. You start with the absurd goal of growing a 400-pound tropical jungle epiphyte on a freezing, urban, concrete balcony.
Right, an environment seemingly designed to kill it.
You defeat the freezing air by calculating the specific heat capacity of water, deploying black thermal batteries and stone mulch to radiate warmth. You defeat the suffocating urban soil by engineering a highly porous matrix of pumice, granite, and charcoal to mimic a limestone cliff. You defeat the violent wind shear and dead weight by driving 316 stainless steel molybdenum wedge anchors deep into the concrete to support a motorcycle tire.
And you defeat the plant's natural yield limitations by deploying Box-Benkin statistical mapping, perfectly timing 650 grams of potassium to artificially swell the cellular vacuoles.
And finally, you defeat the literal rotation of the Earth by rigging a 28-watt light bulb on a timer, resetting the plant's phytochrome system, and hacking its stem cells into believing winter is an illusion.
It is the ultimate triumph of knowledge, math, and engineering over environmental constraint.
We've taken gardening, which is usually a passive, peaceful hobby where you hope for rain, and turned it into an aggressive, calculated act of biological mastery. And if you connect this to the bigger picture, whether you're actually trying to build a dragon fruit fortress on your terrace or you're just trying to keep a finicky houseplant alive in your living room, understanding the underlying why changes your entire perspective.
When you understand why roots rot without oxygen, why physical stress triggers hormones, why light dictates cellular logic, you stop guessing. You stop treating nature as a mysterious lottery, and you start treating it as a system you can diagnose and optimize.
It makes you realize that natural limits are very often just engineering problems waiting to be solved. Which leaves me with a final provocative thought for you to mull over. We've just spent an hour detailing how to completely override the biological evolutionary limitations of a tropical organism. We use thermodynamics, statistical math, and industrial steel to force a living thing to achieve outcomes it could never achieve in its natural state. It makes you wonder, what other natural limits in our own daily lives are we just passively accepting? Our productivity drops, our energy crashes in the winter, our habits stagnate, and we shrug and say, well, that's just my nature. What if those limits aren't fixed? What if they are just waiting for us to stop blaming our nature and finally step up to engineer the right microclimate, the right chemical inputs, and the right structural support for ourselves?
We are fundamentally biological machines as well.
We truly are. Thank you so much for joining us on this incredibly deep dive into the engineering of the natural world. Keep questioning your limits, keep building your systems, and, as always, keep learning.